Here's an example of how we can use roots and logarithms to solve exponential growth problems. So suppose we have a town that's growing exponentially. Populations often grow exponentially. And so suppose we know that it doubles in 7 years. That's the growth rate that we know. It's often multiplying factor by, in this case, 2, every so often, in this case, 7 years. That describes an exponential growth. And we want to know what's the annual growth rate, the percentage growth every year. It increases by 3%, 5%, 20% each year, something like that. And secondly, we want to know if it's now 25,000 people, how long until it reaches 60,000? So how can we answer questions like that? Well, we've talked about we have an exponential growth equation where the new population is equal to the initial times some growth factor, and we'll call that b in this case, raised to an exponent, the number of years. So each year you multiply by b times b times b times b, t times, so that's b to the t. So how can we find the annual growth rate if it doubles every 7 years? Well, if it doubles every 7 years, then that's going to end up being 50,000, 25,000 times b to the 7 years, if t equals 7. And so then we can solve for b. Divide by 25,000, divide by 25,000, and we get doubling in something that we multiply 7 times to get equivalent of doubling. So that's b to the 7th is 2, and the way we answer that is to take the 7th root of that. The 1/7 power of that, the 7th root. And that's exactly what a calculator is designed to do, to find these fractional exponents. It'll calculate some number. When you raise it to the 7th power, you get 2. It's 1 point something, and the calculator has an algorithm to figure that out. You could do guess and check, but let the calculator do the work. And the calculator comes out to 1.1041 for B. So that's a 10.41% annual growth rate. What happens when we try to graph that function? Well, what we get is a population. We get a population chart over here on the left. We get a population on the left here where we start with 25,000, and each year we multiply by 2 to the 1/7. So after 1 year, it's 25 times 2 to the 1/7. After a second year, it's 25,000 times 2 to the 2/7. After a third year, it's times 2 to the 3/7. And so on and so on. And after 7 years, that's 2 to the 7/7. And that's just 2. So we've doubled in 7 years. And so that's what the graph looks like on the right. In 7 years, when we go from 25,000 over 7 years, we go up and we double. We double the amount from 25,000 to 50,000. And then in another 7 years, we double again. So you have this idea of periods, and in 7 years, it's a doubling period. And 2 of those doubling periods, 14 years, is going to be a growth factor of 4, 2 times 2. And you can do this sort of thing with different growth periods. And so we're going to talk about that. How do you change to an annual growth period? That's what we just did. And so an annual growth period, you look down here, you zoom in, and in the 7 years from here to here, it doubles up to 50,000. What happens in just a fraction of that time? In one fraction of that time, in 1 year, down here, we go up a little bit, and we go up by a fraction of that factor of 2. If it only is 1/7 of a period, we only go up by a factor of 1/7 of a factor of 2. And that happens to be 1.1041. So you can talk about growth factors with different periods. The annual growth factor is 1.1041. and the 7-year growth factor is 2. The 14-year growth factor is 4. You can adjust those depending on the context. So the other side of this question is, when will the population pass 60,000? If it starts off at 25,000, how long until it increases? So how do we find that? Well, that's where logarithms come in. When the variable is in the exponent, we need logarithms. And so logarithms work by changing everything to the same base, essentially. There are various techniques you can use with properties of logarithms, but the essential idea is logarithm is changing everything to the same base and taking the exponent. We'll use base 10 in our case. So first of all, you divide to get the exponential part by itself. And this 2.4 means how long until the population is increased by a factor of 2.4. In this case, from 25,000 up to 60,000. And so it's going to be a little bit more than a factor of 2. But it's hard to do that in base 2. What we want to change to is base 10, because that's what our calculator is set up to do as the most common base. And so since we know we can change that to 2.4 is equal to 10 raised to the log of 2.4, because that's what log of 2.4 is defined to be. Log of 2.4 is equal to 0.38, which is defined to be the power you have to raise 10 to get 2.4. And so you can do the same thing on the other side with 2 is equal to 10 raised to the log of 2, because log of 2 is defined to be the power you have to raise 10 to get 2. And so your calculator can figure out what those two values are. And when you do that, using rules for exponents, you multiply the log of 2 times t over 7, and you set the exponents equal. And then it's not too hard to solve for t, solve for time, the number of years. And you get 7 times the logarithm of 2.4 divided by the logarithm of 2. Plug those into your calculator and get an answer that it's a little bit more than a 7-year period. It's 8.836 years.